Good morning, Irvine.
Good morning.
Another happy day.
Yay.
Sunshine in your day. Is it a slightly rainy day? Who got rained on this morning coming in? It did sprinkle a bit on me. Of course, I ride a bicycle, so I take a maximum wetness, right? And you can calculate when you're riding along on a bicycle, what is the flux of the rain that is striking the front of you as you ride, right? You calculate the area, and you've got the speed of the bicycle moving forward. You know the raindrop density. You can calculate the flux of the rain that's being pounded against you. This morning the flux was small, but I want you to be thinking about this idea of flux, the amount of material, the amount of something you can calculate that passes through some surface area. And if I wanted to have the flux on the bicycle, the flux of rain that hit me reduced, what could I do with my body? Tilt, yeah, smaller body, right, lose weight. Tilt the body so that it's got a different angle with respect to the rain, right? So just as when you hold your hand out the window of the car, if you're going 60 miles an hour, the surface area on the front is quite small if you hold it this way with respect to the wind. And then as you build it up, the surface area gets larger. So the amount of air that you impact per second increases. So the direction of the area matters. So what we're going to do is build some concepts today and tomorrow that depend on that kind of perspective. We want to think about the flux through an area, and we get to pick the area, but the flux is going to be related to electric fields, electric forces, and electric charges. So let's first, let's see, at the end of the lecture from yesterday, or towards the end, we had people estimate by lifting and holding the mass of these tubes. And the estimates were around 10 grams or less from the people who grabbed them. Some people came down and measured them after class as well. And I took it over to the lab and put it on a scale. The scale says 65 grams. So the mass is 65 grams. And that made your hair stand straight up today, didn't it? Because you guessed about 6. So it was about a power of 10 different. Now, what happens is you have to sort of build your facility with estimating in a particular range of values on things. And so, for example, last week I had to move a couple boxes for shipping with one of my daughters, and I picked it up and she says, "Oh, Dad, how much does it weigh?" Because she kind of turns to me as, you know, the human calculator. And I said, "Oh, 25 pounds or so." And we got to the Federal Express and they said, "Well, that's 40 pounds. Oh. Either they've got sneaky scales that are overcharging, or I missed my estimate by almost a factor of 2 on that one. And I think that's likely what happened. So you got to get practicing and practicing and practicing. On the other hand, there was one time when I was driving through Lost Wages and stopped at a fuel stop to buy diesel fuel for a truck of mine. And when all was said and done, the fuel and the tank that they're selling it from said I had put in 45 gallons. The tank only held 40. It was not possible. And then I looked around and there were a couple of hoses in the station that had been clamped off by the Nevada Bureau of Weights and Measures as no longer usable. So I went in and I told the guy, I said, "I'm paying what you've got on that, and you know that's a fraudulent pump, because that's 5 gallons more than what my tank will hold." And he said, "Yeah." So, you know, what are you going to do, right? Okay, anyway, 65 grams for this guy, for your measurements, right? But what did we get for the length?
1 meter.
I think we're cool on not a factor of 10 off on that, are we? Right? Okay. So just practice and practice and know that you will make mistakes on it, and it's just a question of building the experience so that you have a little more facility with it in that moment. Okay. So we decided that the force between the two tubes displayed something that looked like this. Let's see what we mean by these different symbols. The force between them went as 1 over the square of the distance. And we didn't prove that it was exactly 1 over r squared, but we did show that it was faster than 1 over r, so that it's got to be something around 1 over r squared. And lots of careful measurements have shown that this is a pretty good measure of this. So that's as if we had Q1 here and Q2 over here, and who knows what they are. They could be plus, they could be minus. So here's these charges at different places, and they are separated by some distance. We got to get into the plus and minus business in just a little bit, but we noticed when we put 2 of the same charge magnitude or same charge sign on both tubes that they repelled. So we know that like charges repel. And the direction of repulsion, was it pushing? It was pushing away, wasn't it? Always away. And who was doing the pushing? Forgot. Cassidy. Cassidy was doing the pushing. And to keep the pushing going, she had to get where it stayed to be pushing away. So the force of repulsion was this direction, right? And what about equal and opposite? Right? So we know that there was, so the force on charge 2 due to charge 1 was, in this case, repulsive, pushing away. So I've written so far a scalar, haven't I? So let's make it into a vector now and put a vector symbol here, and we have this symbol now. Let's do it this way. Yeah, on R12 is pointing that way. Sure. Okay, so what I've done now, see that little R12 with the hat? It's like a little pointed hat. A little pointed hat means unit vector. A unit vector has direction, but its magnitude is 1. So when you multiply by a unit vector, it tells you the direction of things, but it does not change the magnitude of what's going on. So this tells us that it's a force that's repelling away from the other charge. 4 pi epsilon naught. Epsilon naught, 8.85 times 10 to the minus 12, and this is going to be in MKS units. So it's going to be coulombs squared per Newton meter squared. This is called epsilon. It's a Greek letter with a little naught down there. And the naught has special significance. It means that we are in vacuum or free space in the presence of no known matter. No matter is there around this. So epsilon naught. It turns out that the properties of air, for example, are very close to the properties of free space or vacuum for a lot of these kind of circumstances. So you can typically use this number when you're doing calculations about electric charges in air. Not all the time, but typically. Why the 4 pi? Isn't that kind of messy to throw it in here? And none of us would have thought to throw it in here at this moment. It turns out that later it will be convenient to have had the 4 pi in there. So this is the convention that people use because there are some later ramifications where that's convenient. Alternatively, you can use that 1 over 4 pi epsilon naught in a lot of introductory textbooks is written as K, and that's 9 times 10 to the 9th, and that has units of Newton meters squared per Coulomb squared. So you can use either one. I'm kind of old school and I use the epsilon naught. But the books for intro physics often use a K instead. Now the thing is here, you got a 9 times 10 to the 9th or an 9 10 to the minus 12. Those numbers are a long ways away from 1, aren't they? So if you're doing calculations and you forget to put that in there, your number is going to be a factor of 1 billion or more off. So you got to be a little careful in doing some of this kind of stuff. All right, so we take a look at this, and this starts to tell us that there are charges. The Q1s and the Q2s are electric charges, as we will call them. Now, when we rubbed the felt on the tube for doing that demonstration, did you see the charges? No, you didn't see them. I didn't see them either. So that tells you something about how big they are, doesn't it? It tells you that if they are large, they are not visible to the human eye. On the other hand, Cassidy, when you were down here and using it, did you bump into any of them and like it was this large thing, right? No, I don't think so. It's not Mr. Alabazium's world here. Okay, so what we've done now is found that there is some kind of force that is created by things that are small enough we can't see them. So they're microscopic in their size. Now the thing about it, we got your electrons and protons for your common charges that we deal with. And I've been dealing with electrons my whole life, of course. But I've also been dealing with them quantitatively, studying them and using them for more than half of my life. I don't know how big they are. Okay? There are some things that are unsatisfying in life. I do not know how large they are. All I know is they are very small. Okay? And that's a curious problem, but I can live with it. I know how much charge they have, and I know what their mass is. So I'm cool with some of the properties that I'd like to know. But how big they are, I can put an upper bound on it, but I can't put a lower bound on it, and I can't seem to measure it. So we have to live with a little bit of dissatisfaction, but then try to figure, sometimes maybe you get lucky and somebody will figure out how big it is, and then we get another thing to put in the books. But what's in the books is pretty good stuff, and it doesn't come back out, because the way we measure everything, we do know what we've measured and how well we know it. Okay, so electrons and protons. So these guys we're going to give a negative, and these guys we're going to give a positive to. It doesn't matter which way we do this. This is a convention. We're going to decide. We know that they have opposite effects on each other. One of them needs to be positive, one of them needs to be negative then for the math, to do the mathematics. And we are going to choose that electrons are negative and protons are positive. Okay? And then they have the Q, the magnitude of the Q on the electron or the proton is 1.6 times 10 to the minus 19. In the units of MKS, we're going to call this coulombs. Now, this is a curious thing as well. Charges are quantized. You have 1 charge, 2 charge, 3 charge. You do not have 1.375 charges. Doesn't happen. Our observations are that the charges are quantized. And this 1.6 it's right near there. It's not quite that. It's a little off from that, but that's the number I kind of remember. And coulombs. That's the modern day system of units we use for measuring charges. On the other hand, let's see. Do you remember, do you remember this guy? Who is that guy? Benjamin Franklin. Make Ben your friend, right? Benjamin Franklin was an incredible scientist and studied electricity and magnetism. Now, who do you think he got to hold the kite string? One of you guys, right? I have no idea. I'm just making it up. Okay, so what you want to do is, if you look back in history, you'll find, for example, in America, the units for charge didn't used to be coulombs. It used to be Franklins. Everybody kind of comes up with things locally, and Franklin was a leading person in electricity and magnetism, so there was Franklins going around. And so that guy was pretty darn smart guy. Okay, so we have these quantized and are quantized. That comes back to be very interesting when you start actually doing the calculations of small things using quantum mechanics. So you're going to get lucky here. We're not going to do that. Okay. On the other hand, it's very exciting to deal with that. So we're going to deal oftentimes with the amounts of charges. Suppose we had a mole of charges, 6.02 times 10 to the 23rd charges. And if plus or minus one charge on that is a pretty small difference, isn't it? So the relative change is quite small. So for nearly all the calculations you do on a macroscopic level, you don't care that they're quantized. You just care they're quantized when you get down to the microscopic level, dealing with your atoms and molecules and things like that. Okay, so the convention is to have electrons have a negative charge, protons have a positive charge, and the force between different charges is that way. So if it was an electron and a proton, they attract, right? They want to suck each other together and go down to zero radius, radial separation, right? Well, let's see. What's a hydrogen atom made of? A proton and an electron. Well, why don't they just go poof? They're far apart on their scale. Yeah, half an angstrom or so. Wow, big stuff for a lot of things. And they don't go poof. So that should tell you that when you get down to the microscopic level, there may be some interesting physics going on that isn't just what you're knowing at this point. Maybe there are additional forces. Or maybe there are ways that things balance. For example, doesn't the sun attract the Earth? Yes. Why don't we just go poof? Yeah, maybe we will on the long scale. Who knows? Could be bad news, right? A little too much friction as the Earth goes around, and what might happen? Slow down, slow down. If we lost the angular momentum of the orbit that we're in, that would be bad news for that, right? Okay, so we have here for the Earth and the Sun, we don't go poof into the Sun because we've got a balance of that centripetal action versus the gravitational. Balances out, leads to the sunrises, we have palm trees, it's lovely weather, right? Good thing. Okay, so now, when we do this, oh, this is cool. Forces. Now, let's see. Can you help for a second? Can you stand up? Can you stand up? And you are?
Harry.
Harry.
Yeah.
Okay, Harry, Roger McWilliams, and you are? Serena. Okay, I'm going to push on Harry. You ready? And you have to react, right?
Okay.
Okay, if I push, what's the direction that I'm pushing him? That way. So if he doesn't do anything to oppose it, he'll get pushed backward that direction, right? Okay, now, Serena?
Sabrina.
Sabrina. Now you push on Harry. What's the direction? Just give him a push. This push. Yeah, I want to do vector stuff. Push right here.
Oh, here.
And she pushes. What direction is he going to go? To that direction, to your left, correct? Okay, come on back, Harry. Okay, now, if both of us are going to push, how do we figure? How do we predict what his direction of acceleration would be? We add them up, right? Okay, so ready? Now, see, symbolically we're doing it now, and if we both push, then he's helping out because he knows what the answer is, right? So that's the direction he would go, right? So what we have done is in our minds decided we can superposition, add up each of the separate forces to get the total. Thank you, Sabrina. Thank you, Harry. Okay, so what we're doing is by principle of superposition, the force total, right? Force total is going to be by adding up the different forces that we have. What does that little squiggle mean? Sigma. What does sigma mean? Sum. And then you put like I equal 1 to, should I do that? You like that little detail stuff? I equal 1 to what? You like n? Capital N or small n? Small n. Oh, I like the capital N better there. Okay, we put a small n. Keep you happy. Okay, and the n represents what? The number of charges we had to go around and count and add up, right? Okay, alternatively, oh, dreaded. What's that mean? It's a serpent. It bites, right? That's the rattlesnake of integration. You've got to integrate, which means add up all the little differential elements of force to get the total force, right? So if we had a bunch of charges, so we had charge here, Q1, Q2, Q3, and I'm going to put a test charge over here, the one we're interested in. Let's call it a test charge, Q test. What I would have to do is add up the forces on here from one of them, two of them, three of them, right? Like that. To get the total force on that test charge, I'd have to add up the force due to Q1, the force due to Q2, the force due to Q3. And maybe the force due to Q2 has a minus sign compared to the others, so it may be pointing the other direction. So it gets a little hard to add them all up, but you can do that, especially with computers these days. They can do all the hard little stuff like that, and they don't even complain. Okay. Now, let's do some examples. So what we've just described then is that the force of 2 point charges have a falling off that goes as 1 over r squared. 2 point charges, the force falls off as 1 over r squared. Now let's consider a rod. Oh, here's a rod. Look at that, right there. It's just coincidence. Let's put some charges on that. How many charges did I put on there? 9, 7, something like that. You can count them, right? Now instead, let's just keep putting them on there so we got a whole lot of them. And let's say, what's the length of this thing? L. Okay? And L on the diagram here is about 1 meter, right? But it's symbolically going to be whatever it is. And so if I had Q along the rod, and suppose it was distributed uniformly along the rod. How's that? Divided by that length. That tells me how much charge per length. Harry, you wearing a belt?
Yes.
May I borrow it? I don't want to take this one because it's holding the microphones and everything. Okay, we have a belt. Okay, how long is the belt?
1 meter.
About 1 meter, right? Does it have some mass?
Yes.
Yes, it does. Suppose that it was 100 grams, 0.1 kilograms. If we took the belt and chopped it anywhere along it, we see the mass is uniformly distributed. And if I wanted to know how many kilograms per meter, I'd take the total mass of the belt divided by the length, 0.1 kilograms divided by 1 meter, and I get 0.1 kilograms per meter. And so I know if I cut the belt and I take 2 centimeters, that the amount of mass there will be 2 centimeters times that mass per unit length. So knowing the mass per unit length, then I can say how much I've got. When you buy rope at the store, you could buy it by the length. In the hardware store, they sell it by the meter. Or you could buy it by the kilogram. If you know what its kilograms per meter are, and then you say, I need this many kilograms, you will know how many meters you bought, right? Either way. So, thank you, Harry. So this uniform charge like this, we will commonly give that a designation and call it lambda. Here's our second Greek letter of the day. No, our third Greek letter we threw in a pie for fun, didn't we? Okay, now, how is that 3.14 pronounced? Pi, right? That's what we all say. Anybody speak Greek here? No? No, any late Etruscans here? No? No early Greeks? Okay, it's pronounced P. But, oh, excuse me, I already have P this morning. No, I don't think that's going to work in polite company here, right? We're used to saying pi in America, okay? Pi, psi, chi, all those things like that, right? No Greek, there is no long I sound in Greek unless there's a diphthong. Do I look like a diphthong? Okay, so we're going to just call it pi, okay? Now, let's imagine the electric forces that are created by this. We go out somewhere over here. Where shall we call that? Oh, let's call that X. Why not? From this charge where the arrow starts out to where this point is, we'll call it point P. Okay? Oh, no, this is point pi, isn't it? So out there at point P, along that arrow, that one charge that's there is this distance x away. And if we were to calculate the force that it created, that's going to go into the r squared, that distance. Now let's imagine going over here and looking at something coming from over here going down. Is that the same distance as that x label? It's not, is it? So it's a longer distance up, and in fact, let's call that distance y. So we have a recognition then that as y is 0, it's just that distance x out. But as y gets bigger in the plus direction going up, now the distance of the separation of the charges increases. And if we want to find the total force at point P, we're going to have to add it up from each of the charges all along there. Doesn't that look like an integral? Okay, now let's just do ourselves a favor and think about the physics before we do any detailed calculation. Let's try to understand what we expect to get. If the rod is very short, that is, compared to what? If the rod is very short compared to that separation over to point P, then it's as if all the charges were at the same point. Make the rod like this. The distance from the bottom, this thing over, the distance from the top, it's pretty much the same as that. So in the limit of this rod being very short, we expect that it's whatever is the total charge on the rod divided by 1 over r squared, replacing the r squared with x. It goes as a 1 over r squared. So we know that we could make that approximation. If the rod is very short in dimensions compared to the separation, it acts as if it's a point charge for our calculation purposes. Now let's do the other thing. Let's stretch the rod out. Okay? Psychedelic moment. Let's run that rod to infinity and down to minus infinity. Remember, we got plus directions and minus directions. We run the rod way out there. We look at this charge here, and it's going to do a 1 over x squared. We do the charges way out there. They're going to do a 1 over whatever that hypotenuse of the triangle is, distance squared. And they're a long ways out there, aren't they? Are they going to contribute very much? No, it's a 1 over r squared force. As soon as the charge is twice as far away, it's going to have a quarter of the effect. So that means that the charges way up the rod or way down the rod don't have much effect per charge. But let's look at it a different way further. Let's look down here, and let's divide it out into equal angles so that each of these little segments of a pie have the same angle they subtend. As they get further out, what happens to the length on the rod between the pie slice points? It increases. So the length of rod between the pie slice pieces is getting longer and longer the further away you get. So that there's more and more charge in that pie slice but it's further and further away. More charge in the pi slice offsets to some degree the fact it's further away. So we expect for a very long rod, it doesn't go as 1 over x squared, but it goes something like 1 over x. And that's what we're going to find. So we expect it to be something like 1 over x for a long rod. Let's think now. If we're going to look at this point P, what would we like to put there? A charge to feel the force. That's where Cassidy would like to put the other tube, for example. And if we put a charge there, let's put our little test charge there. So there's going to be a force on that test charge. And that's going to be, for each charge, it's going to be the sum, right, of 1 over 4 pi epsilon naught q sub I q test over r squared. And you have to put in whatever the r is going to be, and then times whatever the ri test hat is going to be. I can bring that test charge out of this and just have the remaining. Well, I'm going to replace all of this with a different symbol. And then I want to figure out what it means. And then we'll go back and look at that diagram at point P again. F equals Q test times E. E is for electric field. Electric field. Now you have some experience in mechanics with gravitational fields. They're extremely useful. They keep us at the boundary between air and ground, right? So we don't fly off the Earth, unlike helium, which is lost. Okay, so Q test times E. So let's think about this. Force is on the left. Force. That thing is so important to us. Force on the Q test divided by Q test equals E. Let's look at it that way. The electric field is the force per unit charge. That's what that says. Electric field is force per unit charge. Is a very useful quantity to know and concept to use. The gravitational field at the surface of the Earth, the little g that you're used to using, how do you get the total force on a mass? What do? You times the mass and little g. Total force F equals mg. And you've been using that quite comfortably. Little g is the gravitational force per unit mass. It's a constant, isn't it? And then it's 9.8 meters per second squared approximately. And then you want to know what the total force is. You go, hey, how many kilograms am I accelerating here? M times g. This is the same kind of concept. Force per unit, in this case, charge, not unit mass. So we're going to do force per unit charge. That's the electric field. If you know the electric field at some location and then you bring a charge in, you know you can predict what the force is going to be. Simple as that. So knowing the electric field is extremely valuable, just like knowing little g is extremely valuable. And you know, people take airplanes and little sensors all over the planet to measure little g very carefully, because it's really helpful for finding all the petroleum that's underground. Yes. Okay. Oh, speaking of that, remember we did the calculations with the cars and things. the Prius owners are all helping to explore what direction technologies may go for when we run out of petroleum. It's a very helpful thing, even though it costs more, even though it uses more petroleum to drive a Prius than, say, a Corolla, if you want to compare with those. Over the life cycle of the vehicle, we still need to explore these different technologies and find them. So the Prius people are like the technology checkers, right? The early adopters is what the marketing people call that. And we have to do that kind of stuff. So I urge you guys to go out, buy a Tesla, okay? But even more excitingly, buy a 1902 Baker Electric. Refurbish it. Make it be a moving history museum and enjoy using it, right? Okay? So go out and do that stuff. We got to try the new technology, because if we just sit around where all of us are just driving Ford Model A's, when we run out of petroleum, that ain't going to be a good solution. Right? So you don't want to just do that. Okay, so electric field is force per unit charge. Now we look up here and ask ourselves, what's the electric field at point P? The electric field at that point depends on the contributions from each of the charges. So if we have our rod with lambda coulombs per meter, and here we are at point P, now we could say this little chunk down here that's dy tall has an amount of charge, lambda dy is the amount of charge at that point, and it makes an electric field contribution here that looks like this, right? And, oh, are you getting my angle? What shall we call that? Theta? It helps if you belong to the sororities and fraternities for this stuff, doesn't it? Right? You know this stuff. Okay, so you could talk about the distances here with our y and x, or you could talk about thetas, and now suddenly you got to pick your variables, don't you? Which one you want to do? As y gets real big, what happens to theta? Where does theta start out? Theta's 0 to begin with, right? And then go at the center there, and then the theta goes out to what value? 180. 180? And on this side it goes out to what?
90.
So, and we could use plus or minus 90, or if we wanted to be very elegant, we could use radians instead, right? Pi over 2, minus pi over 2. You want to kind of, none of them are pleasant to use, so you want to kind of practice using them all so you get used to it, okay? Now when you do that then, oh, let's look at this guy. Isn't that pointing up? Okay, now, Harry, Sabrina, up and at 'em. Okay, now let's suppose that I'm over here, and Sabrina, come on, and Sabrina's here. No, let's put Harry here in the middle. Come on over here, Sabrina. Did I get it right now, Sabrina? Okay, you stand here. We're both here, right? I'm going to push this direction. Sabrina's going to push that direction. Exactly mirror image, right? And not hard enough to knock him over, okay? We don't know him well enough to do that. Okay, so now if we push, right? Ready? And we both push. What's the net direction of the force? Yes, Harry's excellent. He's given you the picture, isn't he? It's back, straight back that way, isn't it? Even though I had a component that was off to your right, and Sabrina had a component that was off to your left. Have a seat, guys. When we look at the way this thing is set up, here's this guy down here. Isn't there one up here that's the mirror image, right? And this guy has its own dE over here. Oh, look at that. And what do we end up doing? What happens to the vertical component then in this drawing? It goes to 0. Sabrina's push in that direction and my push in that direction canceled each other, and what was left was just the straight out one. And you get then that the electric field goes straight out and goes like this. Oh, let's put a lambda and a 1 over x. Oh. 1 over the separation, first power, not second power. How did we get from that drawing over to there? By walking 1 meter. So there's some little dots here, aren't there? In the reasoning. You need to do the integral. The integral is done. Oh, I know, but I have some help. It's in the book. They work it out both with the x and the thetas, x, y's, and thetas, show you how to change the variable and how to do it, okay? So you do that. That's going to take you like an hour because you're going to go, oh, the calculus, not the calculus, right? Okay, but then you say, Professor McWilliams, we need some help.
Oh, I will come help with the calculus. I like the calculus.
Okay, so you need to do the calculus, okay? All right, I don't do that too well. Okay, so anyway, do the calculus and you'll get that it goes like that. Now let's take a look at another geometry. I need to take a sheet. Here we go. There. I have a sheet, right? What is the shape of the sheet? Rectangular. And does it have extent towards you guys? No. It's flat. So let's imagine a sheet. Now let's think of a flat sheet. A flat sheet of charge. Okay, so somebody in the back, raise your hand. Oh, good, in the red shirt. Thank you for helping. What's your name? You're the only red shirt. What's that? Nancy. If you look at this sheet from where you are, it looks pretty close to a point source, doesn't it? The charge over on this side of a sheet and the charge over on the other side of the sheet, the distance to you does not change very much depending where you are on the sheet, does it? So if you had a finite sheet like this, and it's small compared to the separation of me out to Nancy, it's going to act like 1 over r squared. You add up the total charge on the sheet, divide by the square of the distance, and you've got the magnitude of the force to, within 1% or even better. Okay? On the other hand, suppose that you were an ant, one of the insects, right? And by the way, in the end, the insects will win. So now, if you were an ant and you were walking around on this sheet, it's not the distance to Nancy, is it? The ant is standing there maybe within a millimeter of the center of this sheet, and it looks to the right or left. What does it see? It sees sheet as far as it can see along that, right? The flat surface there, and so it's very close. But the charge way out at the edge is very far compared to the charge that's right under the feet of the ant. So let's imagine now using a flat sheet of charge. If it is very large, uniformly charged, if it's uniformly charged and we have some big, how do you do this? Maybe like that. Some really big thing, and we're going to be some distance x away from it. And now we're thinking of charges in this sheet. Uniformly charged, let's have sigma coulombs per square meter. Now it's not per unit length, but it's per square meter. Now I have all this charge contributing out here to a dE from a ring, and then I'll make progressively larger rings on here to add up all the area. Or you could do it in little squares and rectangles. However you like to do your integrations, it works out all the same each way. And now the total E, which is adding up the little e's and then doing the magnitude, works out to sigma over 2 epsilon naught if it's free space. Let's look back at this rod. We calculated the electric field over on this side and found that the total electric field points this way, outward. And if we took that point P and we went over on the left in your drawing, that place exists. It's not gone, it exists. And the electric field over on the left would be pointing that way. And so we found the magnitude of the electric field goes as 1 over the distance. Here, you have the sheet. You have the sheet. And Nancy, you're looking at one side of it, right? But I'm looking at the other side. So the electric field on your side points out over here. The electric field on this side points towards the board or into the sheet, depending on the charge sign. So the charge on that sheet sends the electric field both directions. So there's a 2 here. It has no distance dependence because now, as you move out in angle, the amount of charge that's in each ring grows exactly as the 1 over r squared effect for you, and it cancels it completely. So we're going to imagine, here's a sheet, sheet 1. Sheet 1 makes an electric field that looks like this. From sigma being on it. Now I want to put a second sheet nearby. I want to put a second sheet nearby. And I'm going to put a minus sigma on that sheet. Okay? I can do this. I have the chalk in my hand. All right, so I'm going to put a minus sigma over there. And this one will make the electric field pointing towards it. And it will make an electric field pointing towards it. All right. This one made by plus sigma, minus sigma, plus sigma, minus sigma, plus sigma, minus sigma. The electric field is independent of the distance from a uniformly charged sheet. Both of those sheets are there. Now let's add it up. What does that equal? Let's put, here's our plus sigma, minus sigma. Now let's add them up. This is so easy, even kindergartners can do it. What does this arrow plus this arrow equal? This arrow and this arrow. This arrow and this arrow. This arrow and this arrow. You wanted to say 0, didn't you? But you saw they're pointing in the same direction, so they're twice as much, aren't they? So here we have electric field equals 0. Here we have it equal to 2 times the electric field from each sheet. So that's sigma over epsilon naught. And over here we have E equals 0. Isn't that cool? So now you can do this stuff with no trouble and calculate everything you want to do. All right. Now, let's make things go boom. Okay? So let's have some fun with some examples of things and see what happens. Electric field. Have you guys ever rubbed your feet on the carpet and gone over behind your sibling and hit them on the back of the neck? And what happened? They jumped. And you laughed, right? You had it done to you, didn't you? You don't think it's so funny, do you? Okay, so what happens then is when the electric field gets large enough, it can cause the air, in that case, to have some ionization. You can make a plasma. And I'm not talking about the plasma in the blood. The ionized charges there make a plasma when the electric field gets large enough. The air breaks down. It has a mental collapse. It changes state from the gas to the plasma. And the electric field at which breakdown occurs C breakdown, and this is in air, 1 atmosphere, sea level pressure, room temperature, that sort of thing, is about 3 million, let's see, newtons per coulomb. You'll also see that written 3 million volts per meter, but we haven't got the volts part figured out yet to know that. So 3 million. Well, it turns out that's a pretty good sized number, which is fortunate because we don't go around ionizing too much, but we can do it some. So let's do an example where we're going to show you, why don't you drop the screen? Do you know how to do that? Oh, maybe I have to log in or something, I don't know. We're going to do a biology thing here. What we're going to do, this is an electrical tool used for electrosurgery. Does anybody need their appendix taken out? How about your tonsils? Anybody want tonsils taken out? We can have a volunteer.
Are we going to get ice cream?
You get ice cream afterwards? Yeah, I promise ice cream afterwards. I don't have any, but I did tell you trust no one, right? Okay, so this is an actual tool that the doctors use in hospitals. And I had the pleasure of working on this kind of stuff for some years. And in fact, some of my Ph.D. Students have done this stuff in the industry for a long time. So when you go in and have your tonsils out, or some kind of abdominal surgery, or knee surgery, or whatever the different things are called, you can use a knife to cut it, or you can use a plasma to cut it. And there are different kinds of plasmas that can be used. We got your various sparks, arcs, glows, you know, coronas, all these different names for different kinds of circumstances, and some of them overlap in their properties. And they're all in the circumstance where the electric field was large enough to make some kind of ionization and breakdown. So I'm going to turn this tool on, and we'll observe when it's okay. So when this thing, you go in there with it, it's got a shaft to it, and there's some electrical conductors up here at the top to be able to put charge one place and not at another, or return the charge to the tool. So the surgeon can hold this and use it just like a knife, in a sense, you can imagine, right? So here's an example. Let's see, over here. You can get an idea of what it looks like. So the separation there from that center, see the little center? This one's a very simple one, just looks like one wire out there, and then there's a return electrode, it looks like, nearby that's the silvery color, and the separation's about 1 millimeter, isn't it? Something like that. And so you can imagine that could do some work, but do you want a guy just dragging a wire across your flesh? Is that going to do anything for you? Probably not too well. You'd rather use a sharp knife. On the other hand, we can push buttons and put the voltages and electric charges here. And in this case, I'm going to put it in saline solution. See the liquid that's vibrating? Get you the different reflections there? Saline solution. The saline solution has a couple of purposes here. One is it's very similar in its physical properties to what's in the body. So this saline solution is what, well, I grabbed this from some doc-related person I know. I told him to look one direction and I grabbed the bottle. Anyway, he gave me a few bottles to do this stuff with. So this says sodium chloride irrigation, 0.9%. Saline, sodium chloride. So the sodium chloride in there conducts electricity. So it's very important in this circumstance that there be some electrical conductivity, because when we start this thing up, the electricity will flow from one place to another like we saw in the last lecture, over here with our different charges we were moving around. And as it moves from one place to another, there's friction microscopically in the water that's there. And you did the thermodynamics to know that that will mean the water's going to heat. Of where the electrical current is flowing, causing the friction, the water will heat. When the water heats enough, what happens to the water? If you keep heating water up, what happens? From liquid it becomes gas. It boils. And when it boils, it makes a little bubble. When you have that little bubble, it concentrates the electric charge across the bubble and causes the electric field to be much stronger inside the bubble than it was in the water. And when I turned this thing on here in the air, did you hear it go beep, beep? It's going, not breaking down there, not the right conditions, warning, warning, stupid use. These things are dangerous. You need to be careful with them. So when I put this thing under here now and I turn it on, let's see what happens. Can you see something? Yeah? Come on up, do the light stuff. We'll adjust the lights to try and get it. So when the electric field is made large enough because of the boiling of the water, making a small bubble right there, then we get over 3×10⁶ newtons per coulomb. At that point, there's a breakdown. The charges cause some ionization. And what do you see there? What do you see? You can see a little bit of bubble action, and what do you see in terms of colors now? Other than that green, right? Here, we've gone green here, folks. We must be really good with our resources. Okay, what do you see in terms of the light that's at the end of this tool? What colors do you see? You see a yellow, and what other colors? You see that purple haze? You see the purple haze? So you see both a very strong yellow and the purple haze, right? Should we try a different tool? Let's be smart about that. I think that worked, yeah. Let's try a different tool. So, you know, surgeons use all kinds of tools depending on what kind of work they want to be doing. So they will take a different shape tool for a different kind of place they need to work on in the body. Let's see if this one will work for that. Shall we do a little surgery here?
Oh, yeah.
Like I said, in the end, they're going to win. No, here, let's do this. We just did a mathematical calculations with one-dimensional point charge, a line charge, zero-dimension point charge, one-dimension line charge, two-dimension sheet, right? I'm going to project the bug into 2 dimensions. Oh, that ticks him off, doesn't it? It seemed like that's what it was, didn't it? I think it was a tick. So he must have been attracted to the lime color. Okay, let's go. Are you feeling a little dis-ease with some of that humor? Okay, yeah. Okay, what do we see for the tool here? I talk to them. Okay, so let's see. Can you see any of the geometry here? It's got little knobbies there, doesn't it? A bunch of little knobbies. Okay, let's try turn this guy on, see what happens. Do the lights again.
Turn off the lights?
Yeah. Just do all off, see what happens. And, oh, hit the, go over there. No, it's over there, the backdrop one. Next to the red light, to the right of the red light. Just the chalkboard lights, next switch over. To the right, to the right, to the right. Yes, down, down, down. Oh, wrong. Oh, God. Okay, hit them all. There you go. One of them must work. Okay, you can stay there for a sec, do your call. Okay, all right, so what do we see here? Oh, yeah, the bubbles are pretty easy to see here, aren't they? Coming out as monster bubbles. Okay, and you see the same kind of color stuff going on there? But this one will spread it out over a larger area. Let me see if I can get it to... Okay, so that one, you know, we can take tonsils out after class if you want. Okay, lights, let's see what we can get. Okay, so this is a real tool. There are several companies that do this kind of stuff, and maybe if you had your tonsils out, maybe one of these things was used. So it's called Electrosurgery, and the idea is that these tools don't have enough they don't have enough electric field to break down in air, but they do have enough electric field to break down when they're dealing with tissues. This one is designed to do it when the tissue is irrigated, say with saline solution. Okay, now let's get another picture here of electric field. Let's see, we could use a volunteer. This is called a Van de Graaff Generator. Who was the next volunteer going to be? There was a fellow. Is he here? Come on up, come on up. It's your turn. It's your day in the sun. And you are? Ramon. Say it again? Ramon. Ramon? Hi, Roger McWilliams. Hi, come on down here. So let's see now. Why don't you stand on that thing? Now, it is your lucky day that it's humid out today. Right? It's very humid out, raining, and so the Van de Graaff generator has very little jolt to it. It's not going to do much to you. Oh. I regret. Okay, so what we're going to do is imagine this rubber band moving and a little exchange of charge happens as it goes past up here at the top by some little metal feelers. And now take your arm and bring it. Oh. That's about all it's going to do, though, unfortunately. All right. Yeah, too bad, huh? Okay, take your arm and bring it closer. Did you guys see what happened the first time? Probably never do it now the rest of the lecture, right? Okay, so let's get her charged. When we put charge on this sphere, what does the charge do? First, let's think about it. It's a conducting metal. So if there's a charge that goes up there and it's happy there, and then another charge comes up onto the metal, it looks over and says, hey, get out of my space. And the forces push the charges to be spread out on the sphere. They'll move the charges until what condition happens for each charge? Charges will be accelerated, forces, until they're uniformly distributed in some way, and in such a distribution, it's not necessarily exactly uniform, by the way, but they'll distribute until the force on the charge is zero. When the force on the charge is zero, it says, I don't have to move anymore, and it stays there. So that means when the force on the charge is zero, what is the electric field sideways inside this thing? Zero. If the force is zero, there's no electric field. So the charges adjust themselves so that the electric field in the conductor is zero. Okay, Raman, listen, sometimes if I talk a little like that, it'll do another good shot. But this is now it's become a dud, right? How long was the arc, the first one you saw? About how long? What did you...
Maybe like 5 centimeters?
5 centimeters was maybe about what the first arc was. So write down your observation for that. And now it's less, isn't it? If you bring closer, will it do it?
No. Oh.
Yeah, but it was maybe 1 centimeter there, right? Okay, and that's all the extent it's going to do. Now, he jumps when that happens. Why does he jump? Well, how do your muscles act? What causes a muscle to move?
Nerve impulses.
Nerve impulses. Electric impulses make muscles move. So Raman is having a very natural... Hey, this is an organic physics class then.
Yeah.
It's natural. Right? Okay, now tell them what you've noticed about the force as you get closer. Does it get bigger on the hairs?
Yeah.
It does, right? So the force falls off as you move away here. How about bring your hand from up here? Does it do it there too?
Yeah.
Okay,
A
so
bit more on this side.
okay, so let's do this. No, I'll have you do this. I want you to put that guy right there in the top. No, that part.
Oh, this part?
Yeah, stick her on there. And you're going to get zapped. But not much today. Well, let's get that one. Okay, now. Okay. Now, well, no, just move away. It'll do its thing here. There you go. Oh, cool. Now, what do we see? What's it doing? So, now, Raman, bring your arm in a little close on this side. What happened? Now bring it up. Up. Well, let go. Okay, so he has his pet plastic with him now, right? And all of those are now getting a little bit of charge added to them, and then they want to repel each other and feel the electric force of this thing overall, right? So the electric field from this ball is like a hair sticking straight out, radially out. We would do this with some gal's hair, but today is not such a good day. It won't do it too well with your hair, so we won't ruin what you've done, okay? Sabrina, you lucked out, right? Okay, now let's try something different though. You like making a mess, right?
Yeah.
You're a guy.
I don't see why not.
Yeah, why not? All right? Okay, so what's this?
It's like a cup.
It's a cup. Did you have breakfast this morning?
Yeah.
Would you like some puffed rice?
Is it real?
Yeah. It's about 20 years old, I'm not sure.
Oh.
Okay, so take the rod like that, and just, now you guys, you're going to have to, no, not yet, not that,
What?
keep it over there. You guys are going to make some measurements. These are puffed rice. What's the mass of a piece of puffed rice? I don't know. You can come up and get a piece to take it home and try and estimate it. Okay? Remember, you can come up here. Okay, and then here's what he's going to do. Raman is going to touch that top of that, this part of the cup, he's going to put right there. And then the puffed rice is going to get charged. And it's going to get kinetically activated. What do you suppose that means? It's going to move. Your job is to measure that movement. Ready?
Yeah.
Go. That is as dull as listening to a physics lecture. My God.
That's what's happening?
Yeah, this is such a bad day. Boy, talk about having a bad hair day. Okay, let's watch it this way. Well, that was pretty dull also, wasn't it?
Yeah.
Okay, take a rice, hold it there. Yeah, ready, guys? Can you measure it? Put it, just hold it down onto the surface, and then let go. Oh. Okay, I'm going to do that again. How high was the highest one you saw? That's what we want to look. Raman, pull back a little, so unless you want them to get lower grades, then block their view. Okay, you ready? Ready? How high does the highest one go? Whoa, did you see that one? What did it do? Okay. We got to about here on them. Is that right? How far is that?
10.
Make your measurements. Okay, now at the end of lecture, each of you is required to come down and pick up one piece of rice off the floor to take home with you. Okay? To get the mass for the rice. Okay? Raman, you want to eat that?
Did they say it?
I'll watch you and find out.
No, they're not good.
I don't know. It is probably 10 or 20 years old.
Really?
Yeah.
Oh, not good.
When I was in graduate school, there was a place that had a Tuesday night special that sold chicken croquettes and all-you-could-eat buffet for $10. I think they saved those croquettes and used them for years. No one ate them. They just ate the rest of the buffet.
Oh.
Yeah, well, you have student health insurance?
No, I think so.
Yeah, well, you'll find out. Okay, that's cool for that one. Thank you, Raman, very much. Thank you, thank you. The nice thing about most food poisoning is you got to get more than 3 of those little things to get you. You know, you got to eat enough that it can make it before you get it out the other end. Okay, so let's see, what time are we at? Oh, there's still time. The excitement continues. Now, let us do an application. Well, let's look at that example that Raman just did for us and think about it, folks. Okay, think about it. Suppose, let's see, F equals QE equals MA. Then, the acceleration is QE over M. What if the electric field is constant? Constant E. Constant E, then remember a half A T squared plus V naught T plus X naught equals what? Equals having to remember physics 3A, doesn't it? Oh, dreaded past, the past. The motion of a projectile under constant acceleration has these parabola things going on, right? Did I get it right? So we would just put in QE on M here, wouldn't we? Here, do we have constant electric field? Well, the electric field is going to fall off on the scale of the size of this diameter. So it's going to go, it's not quite constant going up here, is it? But you could make a guess, a calculation, an approximation for what the electric field is at the surface, and say it accelerated it, you could figure out what that path is going to look like approximately with this. Does it break down? Sure, a little bit. But it'll give you a ballpark idea from the very start. So you should be able to tell me approximately what the electric field is based on your physics 3A mechanics stuff. You know that it went this high. You know that mgh, the potential energy, it had to have a kinetic energy enough to get that high, didn't it? Half mv squared had to equal mgh or more, because there was frictional loss as well. So you should be able to find approximately what the electric field is based on your observation of how high this thing went. Does that sound like an exam question? Yes, it does, doesn't it? What about this stuff? Oh, this stuff, now that appeals to me because a lot of you guys are bio majors, so you should be aware of and understand the equipment you use. Right? When you got the X-ray machine going, what's the dose? What happens to the tissue? All right, that kind of stuff. Okay, so you can use your standard mechanics now to calculate the trajectory of charged particles in constant electric fields, or you can use it just from straight F equals QE and follow them in varying electric fields in space, but it gets more complicated for that. Where are some examples that we do this kind of stuff? Can you think of things where electric fields accelerate things? Wires. How about, do you ever use a computer that has a little fingerprint thing on it? Okay, I worked on some of those with Authentech Corporation, and when you bring your finger nearby, it changes the electric field, just like when Raman brought his arm near here. And then you can read the difference, the currents that get pulled, the charges that get pulled when you bring your finger across, and then map it all out and see, oh yeah, it was that person. And in fact, you could go do a wax finger, right? Get my finger, take an impression, make a mold, do a rubber finger, Halloween costume thing, and go over and try it. Won't work. Because the response with the electric field is different for a living piece of tissue than it is for a piece of rubber. Even if the pattern is the same, it won't respond the same with the electric fields that are drawn in the little sensors that are there. Yeah, it's pretty neat stuff. Okay. Let's see, when you take your credit card and go swipe, right? You either swipe the goods or you swipe your card, right? So you swipe the card. That moves charges, electric charges that get moved past sensors over here and have little magnetism is the way that we think of how those charges are interacting, and then it gets your ID from that. Okay? Old style televisions used to have the electron beams to make the screen that you'd see. The electrons did like this. They made a plasma and then blasted the electrons at them. Oh, here's a neat one. Fluorescent lights. Another electric discharge. You make an electric current flow that hits mercury. You got to get the electric field large enough to get some electrons flowing. It hits mercury atoms inside the bulb. Mercury is particularly good at giving off ultraviolet light just under the visible light range. And that ultraviolet light hits the phosphors, the white paint on the walls of the bulb, and causes them to go crazy across the entire visible spectrum of light. Fluorescent bulbs are a miracle. One of my classmates from graduate school has worked in the lighting industry. Man, a couple % change in the efficiency of a light bulb changes the world. It's really amazing what you can do with good thinking on that kind of stuff. So fluorescent lights are quite exciting. Okay, let's see, the electric fields. Oh, dipoles. Yes, dipoles. Dipole, what does that mean? Let's do a simple example of a couple of charges that have opposite signs. Let's look at a dipole. Okay, Nancy, you still with me? When you look at those two charges, they're not too far apart compared to the distance to you, are they? So if they're making, one of them is the source of electric fields coming out of this positive one, and the negative one is the sink of electric fields. And then we have Nancy looking way over there. What the positive one would make for the electric field you would see, the negative one will take it away, won't it? So you expect the electric field out by Nancy to be approximately 0. But then we get in close here, where I'm located right now, I'm not far from those charges. So the electric fields actually look something like this in a dipole, two poles, two dipole. The alternative interpretation of the pole, like in different uses of this die, could be either to or of. Okay, and this field then goes like that. And you notice along the axis in between the two, the field is just left-right in this drawing. But then it has the curvature as it gets around to the other sides. And it's very weak out here. So it has a three-dimensional structure. It's not entirely the same way as a sphere of charge. It's got a three-dimensional structure. And it falls off like 1 over r cubed when you're far away from it. Because the two charges almost cancel each other, it falls off faster than 1 over r squared. But dipoles are fairly common, where you get some plus charge somewhere and minus charge somewhere else. And they're extremely common on the molecular scale. They make wonderful stuff in chemistry. And since you know how much chemistry I know, it must be that this is the end of today's lecture. Remember to come down and get your piece of rice, please.